Great. So my name is Luigi Luppino. I am quite randomly appointed the Northern Lights chair for this edition of the NLDL workshop. And today I'm going to talk about my recent work, code-aligned autoencoders for unsupervised change detection in multimodal remote sensing images. So in practice, today I'm going to discuss the problem of change detection using remote sensing data, and in particular why it is important to use multimodal acquired images, and what are the issues that arise by doing so, and what are the solutions to overcome the problems. And in particular, I will discuss my proposed methodology, which is affinity-based code alignment of two autoencoders, and then show some results. So first of all, what is change detection? Is the process of identifying differences in the state of an object or phenomenon by observing it at different times. And in particular, for Earth observation, the idea is to use satellite, airborne, or drone imagery to detect changes happening on the Earth's surface. And this can be done by using two images to detect, for example, sudden events like forest fires, or with the more images, so multi-temporal change detection, to monitor long-term trends, for example, deforestation. We can also discriminate between the use of high spatial resolution images, so to detect changes at object level. So, for example, to detect destroyed building after an earthquake, or with the medium spatial resolution, we can cover larger areas to detect changes at the land cover level. So, for example, the growth of a city, or deforestation, or larger areas. So this is an example. We have an image before and after the failure of a dam, and we can clearly see that the changes affected these rural areas. And we can also have a look at which households were affected. But as we can see, the whole area covered by the changes is not covered because we are using a very high resolution image. So maybe with different resolution, we can see changes at the higher level, at the higher perspective. So in this case, we can see an example of a multi-temporal change detection task, where we see the development of the building site of the Istanbul airport. In this specific talk, I'm going to concentrate on the bitemporal case at the medium resolution. So in particular, why do we want to use multimodal images? So why the use of more than one modality? The problem is that homogeneous data is very limiting, in the sense that using images which are acquired by the same sensor at the same with the same configurations and settings under the same weather conditions is very limiting, because it's very hard to obtain images which are acquired very similarly and then compare them directly. So the idea is that if we are able to compare and to combine images acquired in a different way, then we are able to reduce the time response to a sudden event, or to increase the time resolution of our multi-temporal change detection technique. And of course, this brings more challenges, because especially if we use different sensors, then we are acquiring data which is coming from different physical quantities. And very often, this means that these data are not compatible. They are not directly comparable. So what are the possible solutions? We can perform data transformation, so transform and map data from one domain to the other so that they become comparable, or using similarity measure and local descriptors, which can basically bring insight of the two different domains, from the two different domains. Or we can perform classification, segmentation, and clustering using data from both domains. So here I wanted to show you an example of real data. In this case, there are no changes, but we can already see that if two images are acquired by two different sensors, what we obtain is data which are very different and are not really alike. And in this case, we have some urban areas on the bottom and on the top. And you can already see that by doing different sensors, they really look different. And also the noise distributions might be completely different according to which sensor we're using and so forth. So in particular, today I'm going to present my methodology. It's based on the comparison of affinity matrices to align the code spaces of two autoencoders. The general idea is that if we have two images acquired before and after a change, then we would like to have two transformations which are able to map the two images in as if they were acquired by the other sensor. In this way, we obtain two couples of homogeneous images, so as if they were monomodal, and then they can be directly compared, for example, by image difference or image ratio, and then we can highlight the changes. More formally, if we have two sensors, they might have different number of channels, different number of features. And we have two images. IX is acquired by sensor X at time t1, and IY is acquired at time t2 after the occurrence of the change, which we assume that represent the minority of the image. And another assumption that we have to take is that the two images are co-registered, which means that a pixel in one image and the corresponding pixel on the other image represent the exact same location on the Earth. And these are the only two assumptions. Then, if we have patches, so a subsample of these two images, what we would like to learn is these two transformations, which are able to map the data from one domain to the other and vice versa. And of course, we would like to enforce that these two transformations have the property of cycle consistency, which means that if we perform a transformation from the domain of X to the domain of Y, and then the other transformation from Y to X, the input data should be remapped exactly to what it was from the beginning. Now, in order to do so, we would like to use autoencoders. And I'm pretty sure that you are all familiar with this architecture. So you should also know that if two autoencoders are trained independently, there are no constraints or how to say, there is no guarantee that the two code spaces, the two latent spaces, are going to be aligned. They will develop independently, and there is no matching whatsoever between the two code spaces. So what we would like to achieve is exactly this. We would like to align the two autoencoder code spaces so that when a patch coming from one domain, for example, X, is mapped into the code space, then it can be either retransformed back using the corresponding decoder into the original input space, or transformed by the other decoder into the other input space, and basically transform the images from one domain to the other. So in this case, our transformations are basically a combination of the one encoder and the decoder from the other domain. And we tried to do so, but we found out that this was not enough to align the code spaces. So we had to come up with some other ideas or another trick. And this is what we did. So imagine this specific toy example where we have two images with three clusters. The two images are representing no changes, but they are acquired by two different sensors. So we already noticed that they look very differently. And if we plot the pixels into the feature spaces, we can notice that the three clusters are recognizable, but they are not alike in the two different input spaces. So how can we compare them across the two domains? There's no way that we can compare them. And also, depending on the number of features these spaces have, the comparison might not be even mathematically feasible. So we had to come up with some different ideas. And the idea was to basically evaluate the affinities between the pixels in the two domains. In this way, by evaluating the affinity between each pixel, we obtain values which are comparable because they are scaled between the same range, so between 0 and 1. And they are comparable in this way. So the idea is that once we have the affinity matrices, one from one domain and one from the other, we have each row represent one pixel from one domain and one pixel from, in this case, AIX, and we have another pixel corresponding from the patch Y. And in this way, we can compare pixel from the two domains directly. So we have a measure of how similar they should be in the code space by using this, by enforcing that when these two pixels are similar in this affinity space, then they should be correlated in the code space of the two autoencoders. Now, showing some results. Here we have an example of a forest fire acquired in Texas. This dataset was provided by Volpi at Ali, and we can see the ground truth where the forest fire happened. These two sensors are both optical, but one is Landsat 5, which is having 7 optical channels, and the other one is Earth Observer 1, which is having 10. And here we have the results of the alignment of the code spaces. So what you see is ZX and ZY are the codes of the two images, and we can see that the alignment was achieved. And these are the transformations from one domain to the other and from Y to X. And finally, this is the final results. And on the far right, you can see the confusion map where black represents true negatives, white represents true positive, green represents false positive, and red represents false negatives. So we are pretty pleased with the results. And if you're wondering, these couples of false positives are actually clouds and the corresponding shadow on the Earth. So they were not accounted in the ground truth, of course. Another example, there was a flood in California in 2017, and this is the city of Sacramento. And the image on the left was acquired by Landsat 8, so it's an optical image, multispectral image, with 10 channels plus a panchromatic one. And the image in the middle is a SAR image acquired by Sentinel-1A. And as you can see, this blue area are the it's a flood that happened in 2017. And the ground truth was provided by me. It was constructed by using two SAR images acquired at the same time as image 1 and image 2. Here are the codes obtained after the alignment of the code spaces. Here are the transformation of the two images. And here are the image difference obtained and the comparison with the ground truth. Here there are more false positive and more false negatives, but we can already tell you that in this area there are also rice paddies, which in those periods were flooded, and it's how to say, it's very likely that the whole process was affected by the fact that there were these rice paddies. And here some more qualitative comparison with the state of the art. These two methods were proposed very recently, and the AceNet and the XNet models were proposed by the same group last year. And we can already see that the far right model, which is the proposed one, is competitive with respect to them. The kappa value is a matrix which can go between -1 and 1, and of course, the higher, the better. This concludes my presentation. We proposed a novel method to perform multimodal change detection. It's completely unsupervised, and there are no other assumptions rather than the co-registration of the images. And there are only few hyperparameters. It's applicable to other fields of image analysis, and I'm currently working on applying this to, for example, multimodal change detection in the medical images, so X-rays and MRIs. And the code is publicly available, was developed in TensorFlow, and you can go and check it out. Thank you for your attention.